Hello and welcome to everyone watching this presentation. In this work, we have established a new workflow for multi-well lithofacies interpretation by using petrophysical inversion, unsupervised and supervised machine learning. And this work was conducted by me, Sumit Verma, Subhajit Bhattacharya, Khaled Chaudhary, and Miao Tian. So outline of our work. In this presentation, we will start by giving you the motivation and background of our work, and I will also address the research questions that arise during our research. And then I will show you the study area and discuss about the dataset that is available. And then further, I will describe the methods and the results that we have obtained with our research. And at last, I will give you the conclusions of this study. Since this study is on lithofacies identification, it is important for us to first understand what lithofacies are and why they are important. Why do we want to study them? So lithofacies studies are actually critical for hydrocarbon exploration, CO2 sequestration, geothermal exploration, paleoclimate studies, and some other studies as well. So here I am showing you an example from CO2 sequestration. This is from Sharma et al., where they have studied the potential of CO2 sequestration in Weber sandstone and Madison limestone. So they have divided the lithology in different phases based on their different mineralogical components. So here they are saying that the lithofacies that they have identified, they are sandstone, limestone, high porosity dolomite, low porosity dolomite, and shale. And you can identify these kind of lithofacies from the well logs as well as the core data. And both kind of data combination can give us the best results. So now we need to understand what are the ways by which the lithofacies identification can be done. So core measurements or the measurements on the core samples along with the core description can help identify detailed lithofacies. The core measurements can include, say, FTIR, the Fourier transform infrared spectroscopy measurements, X-ray diffraction, X-ray fluorescence, which can provide detailed elemental and mineralogical compositions, and that eventually provides good lithofacies identification. But the challenge here is the coring is quite expensive, and that is the reason why we do not have that many cored wells in even basins like Permian Basin, where there are thousands of wells are drilled. But alternatively, there are many well logs available which can provide an alternative solution for identification of lithofacies. So we can use physics-based petrophysical inversion on the well logs to identify facies. Such inversion provide depth by depth multi-mineral model where the mineral volumes are available along with the porosity. Also, these petrophysical inversion is generally calibrated by the available core data, which increases the confidence in the identified lithofacies by multifold. So here in the example from North Slope, Alaska, one of the papers that Shubhajit and I have written recently. So this is a multi-mineral model that we computed utilizing different well logs, as well as it was calibrated using the core data. So in our research, we solved two multifaceted problems. One of them occurs after we have obtained the multi-mineral model solution with the petrophysical inversion that we have to convert that to lithofacies. And the common approach of that is deterministic cutoff. But deterministic cutoff is a quite simple way of solving this problem, and it cannot work when there are complex lithologies. For example, if you have calcite cutoff, you can make it limestone, lithology or lithofacies, but then you cannot make a simple cutoff for something like organic rich shale or organic lean shale. Okay, so in order to solve this issue, we use a little bit more complex way, and that is with the unsupervised classification. So we apply this unsupervised classification to the mineral volumes that provides us different kinds of clusters. Now these clusters are supposed to be calibrated, or we have to tie it to some lithofacies, and that we can do by calibration with the core facies. So after this, there is a second problem that we have dealt here in this research is finding the best supervised learning algorithm to find the facies on the wells where this petrophysical inversion is not performed. So for this purpose, we use different traditional and advanced machine learning algorithms, including support vector machine, random forest, neural network, convolutional neural network, and also the LSTM. Our study area lies in Midland Basin, close to Central Basin Platform. And the target formation here is Wolfcamp, which consists of shale sandstone, calcareous mudstone, and carbonate. The data that we have utilized here is from 6 wells, which have a full suite of well logs, along with the 2 core with the measurements, including the core description of lithology and the mineralogy from XRD and the TOC from rocky well pyrolysis. So we start our process by taking well logs on 6 wells and apply or perform petrophysical inversion to obtain multi-mineral model. And this process is guided by the core lithology of 2 wells. This core lithology is obtained by, say, the XRD and rocky well pyrolysis and core measurements. This petrophysical inverted multi-mineral model, we apply a cutoff based method to obtain a lithofacies. This lithofacies is not the best lithofacies because it has certain limitations. So we actually apply unsupervised clustering on the multi-mineral model to obtain more natural clusters. And then this clusters are calibrated to obtain the lithofacies. So this unsupervised lithofacies will be used as a target for the supervised classification training, and this training is done with the different methods mentioned here, and the training is done only on the 5 wells. One of the wells is kept as a blind well, which is not used in this training at any time, and this blind well gives us great confidence on which of these methods works best in the supervised learning for the lithofacies. So coming to the results, I will show you the results on this well, which is shown as a red circle here. And this well was actually used as a blind well for the supervised learning. So it will make sense for me to show you all the results on this well. So in this screen, I'm showing you the physics-based petrophysical inversion, and physics-based petrophysical inversion gives me the mineralogical volumes. We can notice that the majority of the mineralogy here is elite, quartz, and calcite that we can see on here, the inverted log, and there is a small amount of pyrite and some amount of kerogen. But the blank space here you can see on the log that represents the porosity. Further, we used cutoff based parameters or criteria to find out the mineral facies. Here you can see that there are 4 facies that we have obtained by applying this criteria, and these facies are the approximate facies that we want to achieve. And if you look at that here, this is the core lithology, and this facies compares overall fine with this core lithology. So after we generate the multi-mineral model, we use this mineral volumes as an input for the unsupervised facies classification that will generate our final facies. So we tested two methods of this unsupervised classification. One is expectation maximization, the other one is self-organizing maps, and we try to find out the best of these two methods with the optimum number of clusters. And these clusters are then correlated with the mineral facies to find out which method and how many clusters are best suited for our purpose here. So in expectation maximization method, the probability of each point is computed to belong to a certain cluster. If the probability is high enough, then that point belongs to that particular cluster. Otherwise, this point should belong to some other cluster. Whereas in the self-organizing map process, the data from a higher dimensionality space is transformed into a two-dimensional latent space. And the best thing about the self-organizing map is in this process of transformation, the topological order is still maintained. So as I had mentioned before, we had tested a different number of clusters to compare that with or correlate that with the mineral facies to find the best number of clusters with the best method. So here we found the SOM with the 4 facies to be the best number of clusters and best method. So let's try to understand first what is this correlation, how we are working. So for example, we try to correlate each individual EM cluster. For example, cluster number 1, here I try to correlate it with all of these facies, and then I find that this correlates best with the mineral facies 0, or that is limestone. And I would say that EM facies 1 is covering mostly the mineral facies 0. Similarly, we can see the results on the other ones. So here among the two methods, if you look at the SOM with the 4 facies, you can see that this is giving us a best result. You can see number 3 cluster of SOM is covering mostly the facies number 1, whereas the number 1 cluster of SOM covers mostly the 90% of this mineral facies. Okay, so as we have established this is the best method, I will move forward with this. Let's look at the result of unsupervised lithofacies. So here I'm showing you the results of SOM with the 3 clusters, 4 clusters, 5 clusters, and EM with 4 clusters. So we can compare our results here, and then you can see that the SOM 4 clusters is quite matching with the mineral facies, except in few places where it seems to be more consistent with the mineral model here, and it also matches with the core lithology. So here I would like to show the difference between the cutoff based lithofacies and unsupervised lithofacies. So to show that difference, I will plot here the mineral volumes, the 3 most significant ones, elite, quartz, and calcite, against each other, and I would color these points with the lithofacies, or here in this case it's a cutoff based lithofacies. We also call it mineral facies. So here you can see on the cross plots that the points are kind of forming clusters with similar colors. So for example, here with the calcite cutoff, we can see the limestone getting separated quite well, and some other points, some other facies are also showing up really well. But there are few points which are scattered. For example, if you look at the silica rich mudstone, they are quite scattered in different plots. So now let's look at the unsupervised lithofacies crossplot. So here you can see that the crossplot, you have clusters forming, and these clusters have less points which are scattered. So the clusters, when I say clusters, what do I mean by that is the similar kind of properties of those points, they are nearby in most of the plots. So which is a good sign for clustering, and such facies, I would call it more naturally dividing lithofacies compared to the cutoff based lithofacies. So before going into the supervised clustering part, we would like to see how does these unsupervised lithofacies that we had just generated, they look on the well logs, because these are the well logs which will be used in the supervised clustering part. So here what we are doing, we are cross plotting all these well logs against each other and then coloring these points with the unsupervised lithofacies. So now we cannot see any kind of uh, big separation between different lithofacies on any of these two pairs of the well logs. So we cannot use just two well logs to separate out different lithofacies. So there is another thing to look at here is if we look at, say, for example, PE cross plot with 8090, we can see some separation with limestone facies, whereas we can see some other cross plot and we can see the separation, for example, N5 and gamma ray, we can see some separation with the green points here. So we have to utilize all of these well logs and then use it in a supervised clustering manner, and then see if we can get a good blind well testing results that will give us good confidence on our results. Let's move on to the supervised learning. So in the supervised classification, we first perform a training with 5 wells. We keep one of the wells as a blind well, and on these 5 wells we do the training with the different algorithms, the SVM, the support vector machine, random forest, neural network, convolutional neural network, and LSTM. And we refine these models with the best parameters by testing it several times, and then we find the best training models, and then we apply these training models to this blind well, and then the test results are here. You can see the blind well correlation for SVM as 73% and the random forest 72%, neural network 78%, CNN 78% again, and LSTM 80%. So we can notice that here the SVM, RF, which are more traditional methods, they have a slightly lower correlation on the blind well compared to the more advanced methods like NN, CNN, and LSTM. And LSTM here gives us the highest correlation, probably because of its most modern implementation with the memory cell. So here I would like to show you the results with all of the methods applied. So you can see that in LSTM we can find in places where it has better correlation compared to the CNN, and in other places they are more consistent, and overall it shows us a really good correlation. So in conclusions, I would like to say that most of the methods work well when we utilize for supervised facies classification. Out of these, the more advanced methods were the better ones, including the neural network and CNN, and best of those was LSTM, which provided the best facies classification result for supervised learning. And apart from that, I would like to say that the unsupervised ML-based calibrated lithofacies should be utilized whenever you have a complex lithologies instead of using a cutoff-based method. At the end, I would like to thank Fasken Oil and Ranch for providing the dataset, IHS for providing Petra, and ASPI sponsors for providing the financial support. Thank you so much for listening to this virtual presentation. I hope you have enjoyed this presentation and have a good rest of the week. I hope to see you in SCG 2022 in Houston. Thank you.